K, and we had a Galois extension as a capital K, with Galois group G. And for every prime ideal of little k, we had a factorization of the prime ideal in the ring of integers of capital K. This is an ideal, no longer maximal, and it's a product of prime ideals. Ui to the ei, I equal 1 to g. And in the Galois situation, the Galois group permutes the factors transitively. So in particular, gives an isomorphism of their residue fields. This is AK. You take an element that maps QI to QJ, and that maps this quotient to that quotient, so that the residue degree, which is this F, which is the degree of this finite field extension over A mod P, is the same for all the factors, and the E's are the same for all the factors. So this is really just the product of Qi to the E power, and this EFG is the degree of K over little k. Okay, and then for each factor, Q, so Q a factor of P, we defined a subgroup, G of Q, inside of the Galois group, which is just the subgroup that fixes Q. So the index of that is G. And then we had a normal subgroup of G of Q, which we called I of Q, the inertia group, which is the subgroup that fixes Q and acts trivially on the residue field. Trivially on K mod Q. And that has index F because the quotient group maps to the Galois group of AK mod Q over A mod P, and that's a theorem that's a surjective mapping. And in fact, the quotient group is canonically cyclic, we saw. Cyclic group generated by the element we call the Frobenius at Q, which has the property that when you apply it to an algebraic integer in AK, it generates this Galois group here, which is, so it's congruent to A alpha to the norm of P mod Q. So that the Frobenius element generates the Galois group of this finite field. This finite field has Q elements, this has Q to the F elements, and raising to the Qth power on this finite field is a non-trivial automorphism that fixes this field. So we have this situation for every prime P of our number field K. We have a subgroup fixing the factor, we have a subgroup of that, which acts trivially on the residue field, and the quotient group is cyclic. And for almost all P, all primes P, E of P is equal to 1. So we get an actual element in the Galois group, because that would say this group is trivial, and so we have a cyclic generator of this, and this is a subgroup of the Galois group, so we get an element. And the conjugacy class of that is well defined by P. Conjugacy class of GP, of the subgroup IP, and the element FRP depends only on P, not the factor Q that defines it. I'll just do this. I mean, this isn't always defined. Well, this is a conjugacy class that's defined in GP mod IP. And when you pick one of the subgroups, etc. Okay, so that's the situation that Art knew about factorization of primes, etc. And he used that to define an L function. We generalized the L functions that Hecke had studied and that Dirichlet had studied, etc. So the Artinel function. You need one more ingredient. So you need a Galois extension of number fields. You need this theory of the factorization of primes. And you need a representation, a homomorphism from your Galois group to the general linear group of a vector space over the complex numbers, E over C of finite. So a particular example of such a homomorphism is if the dimension of V is 1, that's given by a homomorphism, just by a character, to C star, which is GL1 of C. Right? So characters of the Galois group, that's a special case of a representation, a complex representation. For example, you could take the representation which is called the trivial representation, equals C. Trivial representation. Every group has a trivial representation where you have a one-dimensional vector space and the group acts trivially on it. Or if you had an abelian group, you'd have other one-dimensional representations. Okay, so the definition of the Artinel function. Once you have the representation and you have, okay, so we can restrict the representation to GP. Can restrict. Well, you can restrict V to the subgroup GQ. And up to isomorphism, this group depends only on the prime P in the base field. And so you get a well-defined representation up to isomorphism of the group GP. So these groups are all isomorphic, right? GQ, Q prime, and so you get the same representation of all the decomposition groups. And that gives you an Euler factor at the prime P. So LBS is defined as an infinite product over all primes P, but of the base ring of A. And the term you're going to put in is going to be a polynomial in the norm of P to the minus S. So a polynomial in Q to the minus S. And the degree of the polynomial is going to have to do with the representation V. So I'll just write it down and we'll take a look at it. The determinant of 1 minus the Frobenius at P times the norm of P to the minus S taken on the representation V of vectors fixed by IP. And you take it inverse. So what is this? Okay, so V is this representation which we think of as restricted to one of these groups. They're all isomorphic. And inside of that group, you have the normal subgroup I of Q. And you take the invariance in V of this subgroup, which is a subspace. Vi of Q is a subspace of V. And the vector's fixed by everything in this group. Okay, most of the time, I of Q is trivial. So I of Q is equal to 1. And then this representation is all of V. But in any case, you can always do this for every prime. Now, this is now a representation of G of Q mod I of Q. Because I of Q is forced to act trivially on this. It's of smaller dimension, but it's a representation of this quotient group. And that quotient group has a generator, the Frobenius at Q. Right? So so really you should write it like this. I mean, if you want to be really precise. You take the invariance you restrict V to G of Q, you take the invariance under this normal subgroup, and then Frobenius acts on it. That's a linear operator. You multiply the linear operator by this scalar, you get another linear operator. This is the identity linear operator. You take the difference of those two linear operators on this vector space, and you take its determinant. That gives you the characteristic polynomial of this. Okay? However, the miracle is that this characteristic polynomial depends only on P, because all these elements are conjugate, right? So I can put a P back in. And I mean, to really take the determinant, you'd have to take a Frobenius at Q. And so this is a polynomial of degree less than or equal to the dimension of V in Q to the minus S, which is the norm of P to the minus S power, and then you invert it. And let's see why this brilliant definition, and right now it's just a formal product. It's just a formal product. We're going to see that it actually converges when the real part of S is greater than 1, but we haven't got that yet. But let's see what it looks like in some very stupid cases. For example, suppose V is the trivial representation. Then VIQ is equal to C for all Q for all P2, right? And Frobenius is equal to 1 on VIQ because it's the trivial representation. Okay, so this determinant is just it's just a one-dimensional representation, and you have this is 1, so it's just 1 minus the norm of P to the minus S inverse. So the determinant of I minus Frobenius, the Q, the norm of P to the minus S on VIQ, in this case, just turns out to be 1 minus the norm of P to the minus S. That's it. It's a linear polynomial. It always has degree 1 because the variants are the same for all primes P. And so what do we get for LV of S? We get the zeta function of K at S. Okay, let's do another example. Suppose we have a representation of dimension 1. Dimension of V is equal to 1. So V is given by some character chi of G. And since it's a character of G, it's trivial on the commutator subgroup, so it's really given by a character of the abelianization of G. There may be some field here, K, which is fixed by the commutator subgroup, right? And any character is trivial on commutators, so it's really a character of this abelian Galois extension. Okay, what happens then? Well, again, we have a one-dimensional representation. At the places where this character is ramified, if chi is non-trivial on I of Q, then the space fixed by I of Q is the zero-dimensional vector space. And if it's trivial on I of Q, then it's just the vector space. If I of Q acts trivially, then the I of Q is just equal to one-dimensional. So we get a factor either of degree 1 or of degree 0. And when will we get a factor of degree 0? Well, it would have to be with the prime would have to ramify in this extension. Okay. Well, in that case, so if V is equal to chi, then this product, LVS, is the product over the P, which are non-ramified, because you don't get a factor. If the determinant on a zero-dimensional space is by definition 1, you just get 1 minus chi of the Frobenius at P, norm of P to the minus S inverse, right? Because this is the action of Frobenius at P on the one-dimensional vector space. It's just apply the character. Well, now we saw by class field theory, this is equal to the Hecke L function of a character chi of IF mod PF. Because all the abelian extensions are quotients of this group. And so in this case, we're dealing with a Hecke L function. This is the same as, chi of the ideal P, etc., in the Hecke definition. And so in this case, we're dealing with something that we know satisfies a functional equation, just like the zeta function. So Artin had the great idea that for higher dimensional representations, this would be the correct generalization of Hecke's L functions.
and that this should also have nice behavior. Namely, these Frobenius shouldn't be just random elements in the Galois group. They should be connected enough so that this should not just have a convergence in a half plane. And it does, because the eigenvalues of Frobenius are all of absolute value 1. So every term in this looks like a 1 minus zeta q to the minus s. You have a bunch of terms like that. And those products all converge for real part of s greater than 1, just like the Riemann zeta function did. So it should not only be defined in this half plane, but it should have a continuation like Hecke L functions to the entire complex plane and satisfy a functional equation.
Okay. Okay, so that's what Artin conjectured. That's still one of the big open questions in number theory. So, Artin. So it doesn't always have a holomorphic continuation, because here, for example, the zeta function has a pole at s equal 1. And these Hecke L functions are only holomorphic on C for characters chi, which are not the trivial character. For the trivial character, you get the zeta function. So you prove the functional equation and the holomorphy when you have a non-trivial character, like we did for Dirichlet L functions. So Artin conjectured, if B is a representation, has no invariance under the action of the group. So that distinguishes the trivial character from the non-trivial characters in dimension 1. No invariance under the group. Then LBS has an analytic continuation to the S-plane and satisfies a functional equation with L B star, the dual representation at 1 minus s. So this is the dual representation. If you have a representation of a finite group, then the group also acts on the dual space. That may be a different representation. The eigenvalues of Frobenius are then the inverses of the eigenvalues on the original space. And that's what happened with the characters, right? I mean, this satisfied a functional equation. L chi s satisfied a functional equation with L chi bar 1 minus s. And this is the dual representation in that case. Okay? So we're now going to do a detour. Brouwer proved part of this. Brouwer proved it had a meromorphic functional, a meromorphic continuation to S and C, and the desired functional equation. And we're going to see how Brouwer did that by reducing it to the theory of Hecke L function. And to do that, we have to do a complete detour, leave all this number theory, and once you have this definition, we're going to leave number theory and we're going to study the representation theory of finite groups. Because that's what you need to at least do Brouwer's work. However, the question remains, and you'll see at the end of this little detour, what's the mystery element? Why are these functions holomorphic? They're known in the one-dimensional case to be holomorphic, under that assumption that you're not the trivial character. But that's the big open question that remains. Continuation. Okay, so tour of the representation theory of finite groups. Now, fortunately, Artin knew the representation theory of finite groups. And I say it's fortunate because the representation theory of finite groups was only developed the beginning of the 20th century by Frobenius. And it was a subject which was kind of self-contained. I mean, you had the work of Frobenius, and then his student Isaac Schur, and then grudgingly you had the acceptance of Burnside, who initially rejected the whole thing. And they had all kinds of applications
to finite group theory. For example, they were able to prove using the theory of group representations that a simple non-abelian group had to be divisible by, its order had to be divisible by 3 distinct primes. But it was completely inside of group theory. Artin was the first person to apply any theory of representation in finite groups to anything outside of group theory. And it was to this. And nowadays that seems unbelievable because you need group representations for everything. But at the time they weren't so well developed. So we'll do a little bit of Frobenius and Schur's theory and then come back to Artin. So we start with a finite group and a complex vector space of finite dimension. And a representation is nothing but a homomorphism from G into the automorphisms of that complex vector space. So it's taking your group and viewing it as a group of linear operators under multiplication. There are people that study permutation representations, the homomorphisms to the symmetric group before Frobenius, but Frobenius was the first person to really systematically study this. Okay, so if you have two representations, we'll define a complex vector space with G homomorphisms from V to W. So that's all the linear operators that commute with the action of G, namely T of GV is G of TV, where this is the action inside of V and this is the action inside of W. So you can, that's equal to, if you want to think of it, the complex homomorphisms from V to W fixed by G, where you have to say how G acts on a complex homomorphism, and I'll let you do the conjugation action to make this work out like that. So therefore, it's a subspace of the complex vector space VW. So it's a finite dimensional C vector space. So for any two representations, you can compare, you can see if there are any maps between them. All right. So Schur discovered a very nice property of this Hom space. So we'll call V an irreducible representation if the only G-stable subspaces, W and V, are the obvious ones. The zero subspace and W is V. So there are no sub-objects that form G representations. Now that's analogous in the theory of vector spaces to, if you forgot, if G is equal to 1, the trivial group, then a G representation is just a complex vector space. What are the irreducible vector spaces? They're just the lines. It means the dimension of V is equal to 1. If you think of a complex line, the only subspaces of it are the line and 0, right? But it turns out that because of, when you introduce a finite group, you get a lot more interesting irreducible objects than you do in the category of vector spaces. But Schur proved that they act a little like one-dimensional vector spaces because you have the following result. So I'll just keep listing results in the theory of finite groups, and we'll prove a few of them, and then so the first thing is if V and W are irreducible and not isomorphic. Oh, I should have said two representations are isomorphic if inside of Hom GVW there's a linear isomorphism, namely if there's a T which is invertible that takes V to W, which satisfies this. So suppose they're not isomorphic. There's no linear T that maps. I mean, you can still have a map between, I mean, if you had a subspace, then the inclusion of it in V would be a G homomorphism. But V is irreducible, so you don't have subspaces. They're irreducible, not isomorphic. Then there are no G homomorphisms between them. If they're isomorphic, then the G homomorphisms from V to W form a one-dimensional vector space. So it's either 0 or one-dimensional. Just like for Lorentz. Okay, so that's sometimes called Schur's lemma, and it definitely simplifies the theory enormously. So the reason is this. Suppose I had a map between V and W, a G homomorphism. Okay, well, the kernel of T is a G subspace of V, and the image of T is a G subspace of W. Now, V and W are both irreducible. The kernel of T is either 0 or all of V. If it were 0, that injects V into W, right? That's a problem, because that would give a G-stable subspace in W. So the kernel has to be all of V, or if the image of T is either W or 0, if the image of T is W, that surjects V onto W, blah blah blah. So the image has to be also 0, so T has to be the 0 maps. Did that okay? Okay. So that implies kernel of T equals V, image of T has to be equal to 0, and therefore T has to be the 0 map. So that's this. On the other hand, if they're isomorphic, we want to compute this space. Well, since W is isomorphic, it suffices to compute this space, from V to V, using the isomorphism. So suppose, now I clearly have elements in G from V to V. Namely, I'm going to claim that this is equal to C times the identity map. The identity map is a homomorphism from V to V. It means with everything. So are scalars times the identity. Why is that it? Well, take a homomorphism T from V to V, and take an eigenvalue lambda, an eigenvalue of T. Now you have eigenvalues, well, let's go for the complex numbers. I mean, T is actually semi-simple, but never mind. For any complex linear transformation, you have an eigenvalue. And consider now T minus lambda times the identity. Okay, that's again a G homomorphism, because T is a G homomorphism and lambda times the identity is a G homomorphism, so this is a G map from V to V. It has a non-trivial kernel, right? Because lambda is an eigenvalue, so there's an eigenvector in the kernel. The kernel is a G-stable subspace, and since the kernel is non-trivial, it says that the kernel has to be all of V. So this has to annihilate V, so T has to be equal to lambda I on V, and that's the proof of Schur's lemma. Okay. 2. Here's something that Hermann Weyl found a really good proof of. In vector spaces, if you have a subspace, you can find a complement. The same thing happens for G representations of G over the complex numbers. If W in V is a G-stable subspace, then there is a G-stable complement W prime such that V is the direct sum of W and W prime. Namely, it's a sum of subspaces, and G preserves W and G preserves W prime. Okay, so here's Hermann Weyl's proof, which is very cute and uses the complex numbers. There are algebraic proofs that don't need the complex numbers, but this is so nice, so why not? It says, well, take a positive definite Hermitian inner product, anyone, from V cross V to C. So just choose one. Any complex vector space has many Hermitian products. You can choose a basis and take the standard one. Okay, that has nothing to do with the group G, but make this G invariant by taking the sum. Let's call it this way: V W is equal to the sum over elements in G. G of V, G of W. It's a finite sum, so no problem. okay? So that's still Hermitian, namely it's linear in the first variable, antilinear in the second variable. It now has the property that this is equal to g of v, g of w. And it's non-degenerate because it's still positive definite. If you take the inner product of v with v, that's the sum of the inner product of g of v with g of v, that's a positive real number, and if you sum positive real numbers, you get another positive real number. So it's an easy way of making an invariant Hermitian inner product. Okay, and then take w prime equal to the orthogonal complement of w in V with respect to this Hermitian inner product. And that's a G-stable subspace because the inner product is invariant. And it has this property by properties of the orthogonal complement. So that's a nice thing that works in complex vector spaces by taking an average. Okay. Corollary, that's number 3. Corollary of 2, 3, every representation of G decomposes as a sum of irreducible representations, namely that V is the direct sum over irreducible Wi of Mi Wi, where you might have to repeat something. Well, you just keep decomposing it. If it's irreducible, then it's of this form. And if it isn't irreducible, you find a subspace which is stable, and you take its complement. So now you have it decomposed like this. And if this is irreducible and this is irreducible, you're done. And if not, you factor in the subspaces and complements, and you keep going. But what's cool is that the multiplicities of these irreducibles don't depend on how you got them. Namely, you might think that, but this decomposition process, you might get different factorizations of the representation, but you don't, because these multiplicities are the dimension of the homomorphisms over G of Wi into V. And the reason is by Schur's lemma that if you hammed a Wi into Wi, you get a one-dimensional space. So the ham of Wi into this is m-dimensional. And whereas if you put a Wj here, the ham of Wi into that Wj component is 0. So that this decomposition, at least the irreducibles that occur, their multiplicities are well defined by V. Depends only on Wi and V. Okay, we're almost there. All right, now finally, there's a wonderful representation which contains every irreducible. And that's called the regular representation. So, fine, so we're up to 4. Let V reg be equal to the representation of G on the direct sum of over elements in G. You put a basis vector for each element on that complex vector space, where H of EG is E of HG, for example. So it just permutes the basis elements around. So the matrices are permutation matrices. This is called the regular representation of G. The dimension of this representation is just the order of the group. Okay? So the theorem is that the decomposition of that representation is a sum of irreducibles. You get the sum over all irreducible representations. There are only a finite number of G. And you put the dimension of the irreducible as its multiplicity. So every irreducible has dimension at least 1. So the regular representation decomposes as a sum of irreducibles, and the multiplicity is their dimension. And consequently of that, there are only finitely many irreducible representations of G. And Frobenius determined that the number is the number of the conjugacy classes. I mean, they had the abelian case in front of them. So in the abelian case, all the representations are one-dimensional. And there are G different, the number of characters is the order of the group. We saw the character group had the same order as the group. And the regular representation decomposes as the sum of all the characters. The dimension is all 1. And in the abelian case, the number of conjugacy classes is the number of elements. So in the abelian case, they knew this. But in the non-abelian case, this took a little bit of work. And it took a while for Frobenius to realize it. So let's do an example. The first non-abelian group is the symmetric group on 3 letters. And that has 3 conjugacy classes. It says the conjugacy class of the identity. It has the conjugacy class of a transposition. And it has the conjugacy class of a 3 cycle. Right, so there should be 3 irreducible representations. And the 3 irreducible representations is a trivial representation. You have another representation of dimension 1, which is given by the sign character. So you take a homomorphism from S3 to plus or minus 1, where the kernel is the alternating group. And finally, you have a third representation of dimension 2, which you can get by taking the action of S3 on a 3-dimensional vector space, permuting, so write this maybe as the symmetric group on 1, 2, 3, or maybe let's call them something. Yeah, all right. So this is the action on a hyperplane in CE1 plus CE2 plus CE3, where the group acts by permuting the basis elements, again by permutation matrices, and you take the hyperplane where the sum of the coefficients is 0. Sum of AI, EI, I equal 1 to 3, such that the sum is equal to 0. And that gives a 2-dimensional subspace that's stable under all permutations. And that's our 2-dimensional representation. And so the regular representation in that case, which is 6-dimensional, is the sum of C plus C sine plus 2 times this representation of dimension 2. And the corollary of this, which Frobenius loved, was that the order of the group was the sum of the dimensions of the irreducible representations squared. So here we get that 6 is equal to 1 plus 1 plus 1. Okay. One more thing I need. So Frobenius made a beautiful study of the restriction of representations to subgroups. And that's what Arthur is really going to use. Then we'll go back to number theory. Okay, if you have a representation V of a group, and you have a subgroup of G, you get a representation of the subgroup just by restricting from G to H of V is a representation of H. For example, if H is the trivial subgroup and you restrict it, you just get a complex vector space. That's a representation of the trivial. All right, so Frobenius discovered a method of going the other way. So if you have a representation W, a representation of H, Frobenius constructed a representation called the induced representation of G. Here, this restriction representation is just on the vector space V, so it has the same dimension. This, the dimension, is equal to the dimension of W times the index of H and G. It's essentially a permutation representation on the cosets of H. Well, if W is the trivial representation, then in H to G of W, or C, is the permutation representation of G
on G mod H, on the cosets. That's what this is, by the way. This W3 is the induced representation from this subgroup, maybe, yeah, I'm sorry. This W3, sorry. This permutation representation here is the induced representation from S2 to S3 of the trivial representation, because this is the permutation representation on 3 elements. Okay. And Frobenius proved there was a relationship between induction of representation and restriction of representations, which is the big theorem which is called Frobenius reciprocity. And that theorem is this, that if you have a representation, say, U of H, and you want to compute the homomorphisms over H from U into the restriction from G to H of V, so you want to compute that complex vector space, that's isomorphic to the homomorphisms over G of the induced representation from H to G of U with V. Particularly, they have the same dimension. So let's take the simplest example. Let's take the representation C of H. It says that the H invariance is so what's the dimension of this space? So that would be the homomorphisms from the trivial representation into this. That's just the dimension of the H invariance in V. Is equal to the same as the dimension as the homomorphisms over G of the induced representation from H to G of the trivial representation V. So it says that the multiplicity of any irreducible representation in this permutation representation is just the dimension of fixed space under H. So in H to G of C is the direct sum of the irreducibles W of G, the dimension of W fixed by H times W. And we can see that this permutation representation, the regular representation, is nothing but the induced representation from the trivial group to G of C. It's the permutations of G on itself, not on the cosets. And consequently, so we have a generalization of this formula. This says the dimension of W fixed by the trivial group is just the dimension of W. And here's the general formula. Okay. All right. Good. Now, back to number 3. So Artin proved a number of things about Artin-L functions that allowed him, or at least he thought it would allow him, to reduce to the abelian case. Artin had the feeling, and expressed it many times, that one should be able to prove all of his conjectures just by reducing them to the abelian case. He thought if we knew enough about the abelian case, one-dimensional representations, we should have enough to be able to prove his conjectures on this. He was wrong, but he was partially right. The first thing he proved is if you took the L function of the direct sum of 2 representations, and this is obvious, you got the product of the 2 L functions. Well, that's because the characteristic polynomial on the direct sum of 2 spaces is the product of the 2 characteristic polynomials. So it's true term by term in the Euler product. And the second thing he proved, so that's a formal property of Artin-L functions, and the second thing he proved was this. Suppose you had some subfield, M, between K and little k. And this Galois group, remember, was G. So giving a subfield is just the same as giving a subgroup of G. Okay? And we had a representation of H, U. So because we have a representation of H, we can make the Artin-L function with respect to this base field M of US. So
that's a product over prime ideals of M, not of K, but over M. And Artin proved that that was the same as the L function over little k of the induced representation from H to G of U. Yes. Okay. So in particular, if we could write our representation as coming from characters, namely if U is dimension 1, if dimension of U is equal to 1, we know that this L function has a holomorphic continuation by Hecke's theory, right? And therefore this L function would have a holomorphic continuation. And that works great for a lot of representations. For example, the first representation we had of dimension bigger than 1 was the two-dimensional representation of S3. Well, what happens in the S3 case? Well, here we have this S3 extension. Okay. How do we get the two-dimensional representation? Well, this fixes a field here, M, which is fixed. Well, let's do it this way. Here's the S3 extension. We have the alternating group on 3 letters. And here's our fixed field, M, which is a quadratic extension of K. Something, okay? And if we take, it turns out that this two-dimensional representation, W of dimension 2, is induced from a character of order 3, either 1, of H. Namely, if you take a cubic character of this group is order 3, and which is non-trivial, and you take the induced representation, you get this. And so from the point of view of M, we would know that we were dealing with a Hecke L function, because it's a Hecke L function of a character. And so we get it for this W2. So maybe every representation is induced from a character of a subgroup. That would be very nice. But that turns out not to be true in general. However, Artin had some hope that it might be the sum of representations induced. Namely, you have a lot of subgroups, a lot of subfields. You have all kinds of characters of these groups. Maybe by putting them together in this way, see if you could prove that each of these were holomorphic, so is the product. Well, Brouwer couldn't prove that, but Brouwer proved the following. That turns out to be false. What Brouwer proved is that every representation suffices to the irreducible representation. V of T has the form V isomorphic to the direct sum of Mi induced representation from Hi to G of chi I for one-dimensional representations, where the Mi are integers, but not necessarily positive integers. What do I mean by this isomorphism? It means that if you took the negative part of this and you took it over to this side, you'd have an isomorphism of representations. Okay? So what does that mean? That means, if you use this too, it means that LVS is the product of L Mi chi is to the Mi power, where some of these are in the numerator and some of these are in the denominator. Okay? And that is how Brouwer proved that this has a meromorphic continuation, because each one of these has a holomorphic continuation, and some of them are in the numerator, some in the denominator, so the ones in the denominator could create poles, but in any case, it's meromorphic. Okay? And Artin's conjecture that this is holomorphic is reflecting the fact that the L functions in the denominator, their zeros somehow are canceled by the zeros of the L functions in the numerator. And nobody understands that at all. So that this way of sort of attacking Artin's conjecture is just too mysterious. Good. Let's see this Artin L function machine in some action here. Yeah, let's use the 1 in the following case. Let's take the regular representation, and we write it as the direct sum of irreducibles, the dimension of Wi, that says that L of V reg S is the product of L W S to the dimension of W over the irreducibles of G. But on the other hand, what is this? This is the induced representation from the trivial group to G of the trivial representation. So that's the same by this thing as the trivial group, the M field is K. So this is just equal to the zeta function of K S. Remember, we saw the zeta function of little k gave us the trivial, was just the trivial representation. So this is the zeta function of capital K. So what does this look like? This looks like the zeta function of little k s, that's the trivial representation, times the product of the irreducible representations W, which are not the trivial representation of LWS, the dimension of W. Now the ones that aren't the trivial representation are exactly the ones for which Artin's conjecture is supposed to be true, right? Because they have no invariance. They're irreducible representations. So this product is supposed to be holomorphic in the whole complex plane. All right? These functions are meromorphic in the complex plane, but they both have simple poles at s equal 1. So Artin said, well, if I believe my conjecture, that would imply that zeta k s over zeta s is holomorphic. Maybe the poles cancel, and, right? Or you could, or in the sense of holomorphic functions, this function divides this function. And that's, again, it's a weird statement. It says that every zero that appears for this function appears for this function. Right? So this part you could prove without proving all of Artin's conjecture, because maybe there's some cancellation between zeros and poles here. Right? And for Galois extensions, this was proved. But it should also be true for non-Galois extensions, because look what happens for a non-Galois extension. Let's take any extension of capital K, call it M, and let capital K be the Galois closure. Then M corresponds to a subgroup, right? The zeta function of MS is the same as the L function of the induced representation from H to G of the trivial representation, S. And we saw what that is. That's the product over the irreducible representations of G, the L function over this little field K, of L of W, S, the dimension of W fixed by H, because that's what this representation decomposes as. Okay? So again, this always contains the trivial representation, the dimension of W fixed by H is 1. So this contains the zeta function of K, S, times the product of the other irreducibles, LWS, the dimension of W fixed by H. And so this is again supposed to be a holomorphic. So it says for any extension of K, the zeta function of M should be divisible by the zeta function of K. So that's even harder, that's harder to prove than for Galois extensions. Okay. So for example, let's do, yeah, I like that one. Let's do the non-cubic, so let's take K and make a cubic extension, M, which is not Galois. So the discriminant is not a square, so we join the square root of the discriminant. We get a Galois extension, A, where the Galois group is S3. What is the zeta function of M? Well, by Artin's decomposition, you take the product over all the irreducibles, and you have to figure out what the dimension of the space of W is fixed by H. Well, H now is a group of is of order 2. It's generated by a 2-cycle. Okay? Now the 2-cycle fixes the trivial representation, and on the sign representation, the sign of a 2-cycle is -1, so involve the sign representation. And on the two-dimensional representation, the two cycle has one eigenvalue of +1 and one eigenvalue of -1. You gotta believe me on that. And so this turns out to be the zeta function of S times the L function of this two-dimensional representation. Two-dimensional S. Without multiplicity, because the multiplicity is 1 for both of them, and it doesn't involve the sign. And in that case, we can see that the zeta function divides the zeta function of M, because this is an induced representation from a character, right? This was in the L function of another field, this discriminant field, of a character of order 3s over K through D. So this is holomorphic by Hecke's theory, so therefore the zeta function divides. But if you get to a quintic extension, where the Galois closure is A5 or S5, we don't know this. Okay, so the future. What is the future? So the modern approach to Arden's conjecture is not by Arden's methods to try to write the representation as a sum of irreducible induced representations of characters, but rather to try to understand, at least for irreducible representations, what the analog is of class field theory. You see, for one-dimensional representations, we said, well, we can rewrite this L function using this homomorphism from the ideal group to the Galois group, and that takes the ideal P to the Frobenius at P, and we get a function on the ideals, and that we know how to deal with. Okay, so people started asking, do Arden L functions appear somewhere else in mathematics, like Hecke L functions that didn't make any mention of Galois groups? They just made mention of these class groups. Do they appear anywhere else in mathematics? And it was discovered in the 60s, and it's amazing that it took this long, that they were related, at least when the dimension was 2. You see, abelian cases, the dimension is 1. So if the dimension of B is 1, B corresponds to a character, and LVS is equal to some Hecke L function of a character of A star trivial on K star. So who knew that the next case to study was when the dimension of V was equal to 2? You see, Arden did a lot of study where the Galois group was the alternating group on 5 letters, because that was the first case where not everything was induced. But the alternating group on 5 letters doesn't have any two-dimensional irreducible representations. Its smallest irreducible representation is dimension 3. If you want to get to something that has 2 dimensions, you have to consider the double cover of the alternating group on 5 letters, which is the binary icosahedral group of order 120. And this has a representation of dimension 2. And this goes into SU2, and this goes into SO3. So somehow or another, from the point of view of the dimension of the representations, which turned out to be the way to look at this, it was better to study Galois groups of this type than Galois groups of this type. Who knew? Okay, so from dimension of V of 2, it seems we now understand that LVS is related to the L series of modular forms. Well, in this case, modular forms of wave 1. And modular forms, in Langland's perspective, come from, you might say, they come from representations of GL2 of the Adels. And you can't say trivial on GL2 of K because it's no longer a normal subgroup, right? With a linear form fixed by GL2 of K. So that's what's called an automorphic representation. And these are infinite dimensional. These are one-dimensional representations of A star. And a one-dimensional representation with a fixed linear form means that this group acts trivially on it. And here you have to do infinite dimensional representations of GL2 of the Adels with a linear form fixed by this. And if you went to dimension, and that's already too hard for us to do, if you went to dimension 3 or 4, you take infinite dimensional representations of GL3 or GL4. So that was a huge perspective that was brought in by Langlands. And Tate always said it was amazing that Artin and Hecke didn't see this, because Hecke, at the same time Artin was defining his L functions and working out examples, Hecke was working with the L series of modular forms of weight 1, which have Euler products where the general term is quadratic polynomial in p to the minus s, just like this is for dimension 2. This is a quadratic polynomial. And why they didn't speak to it, they were both in Hamburg. I mean, they were down the hall from each other. And why they didn't speak to each other about the work and realize that they were doing the same L functions. And Hecke was proving functional equations for the L series of modular forms. But they didn't. And it required a sort of a general perspective to see this, which is what Langlands had. So this is why you want to learn about modular forms, because you want to prove Artin's conjecture. And even I think in the dimension 2 case, maybe it's known now for the rational numbers or for totally real fields, but it's certainly not known in general. I should say that it sort of divides up in this two-dimensional case is very nice, because if you have a representation of your group into GL2 of C, you can map it down to the quotient group PGL2 of C by dividing out by the center. And so you can take the image of G in PGL2 of C, right? Let's call that G bar or something. And that's a finite subgroup of PGL2 of C. But we know all the finite subgroups of PGL2C because the maximal compact subgroup of PGL2C, which contains all finite groups, is SO3. And we know all finite subgroups, this is the same as SO3 of C. And it has a maximal compact subgroup, SO3, the positive definite SO3 of R, and the compact subgroups of that, the finite subgroups of that, are the things that stabilize regular polygons. So you get cyclic groups, you get dihedral groups, you get A4, S4, A5. So these finite groups are always either cyclic, dihedral, A4, S4, and A5. And these cases, one knows how to start with a Artin-L function and produce the modular form of weight 1. That goes really back to Hecke. And these two cases were done once Langlands understood what was going on. But this case has been very resistant because it's an unsolvable group and you can't get there by taking a collection of cyclic extensions, etc. And so that's the hard case where this Galois group is the binary icosahedral group, and you take this two-dimensional representation of it. And well, that's a situation for two-dimensional. For three-dimensional representations, of course, there are many more finite groups. For example, the finite group of order 168 has a three-dimensional representation. We don't know anything about its Artin-L functions and things like that. Okay, so I'm going to stop here on Artin-L functions. But it turned out that this formalism of using characteristic polynomials of Frobenius as acting on the representation or acting on the representation with invariance of the inertia group turned out to be remarkably successful in defining a whole host of other L functions, but not for complex representations of finite Galois groups, but for what we call L-adic representations of infinite Galois groups. And last week I'm going to show you some examples of that, starting with the cyclotomic character, and then I'll do the L series of elliptic curves, because that's this whole area that Artin opened is now a vast area of mathematics, conjectures, relationships with automorphic forms, the Langlands program, and attempts to prove things about the functional equations. So we'll do that next week. Good? Good. And I think I'm going to give a course next year, but I'll take your advice because you'll be my audience. I have to give a course every year But there are no courses here in representation theory. So I thought I'd give a course maybe just in representations of finite groups and compactly groups, and maybe non-compactly groups, so we can do it on one course. I know many of you have seen this representations of finite groups, but as I say, in Arden's time, it was a revelation that this theory could be used to prove anything else. Okay?